Okay, hello. This is the theory for chapter 12, which is the kinetic energy of rigid bodies. Right? So we have looked at rotational motion. We need to look at energy now, right? So we know that kinetic energy is half mv squared, but what is it in the rotational, right? So let's see here. Imagine we have some weird looking abstract body like this, right? It has a center of mass or center of gravity here, right? And we're going to denote this as G, like so. And then let's just say we have some position vector R here. And we have a rotational, like so, of omega. And I forgot to get a hotkey for omega. Oops. And then we have our velocity going this way, right? And then in this area, we have a negligible, not negligible, but a very small amount of mass, dm, right? And that's our basis here for what we're going to be doing. So we want kinetic energy for the particle, right? So we have a dt, which is an infinitesimally small kinetic energy, is equal to half dm v squared, right? And so this is equal to a half. We know that v is omega r, so omega r squared dm. And now if we were to integrate both sides, we get that t is equal to half omega squared r squared m, right? Like so. And that is the kinetic energy for the entire body, right? Now, something we need to know, and this is going to help a lot with calculations, is something called the mass moment of inertia. So we have an equation for the mass moment of inertia, and it's the integral of r squared dm is equal to I, right? I is the symbol for moment of inertia. So from F equals ma, if we recall F equals ma, it's a measure of resistance to acceleration, right? That's what a force is. That's what the mass is in that equation. The moment of inertia is a measure of resistance to angular acceleration, right? So you can calculate it about different axes, but it's usually about an axis that's passing through the center of mass and perpendicular to the motion. So we call that I sub g. I sub g is what we call that to represent that it's about the about the center of mass. So, like I said, I inertia here, so moment of inertia, or just I in this case, is a measure of resistance to angular acceleration, right? And we can calculate it through any axis we want, but we're going to use an axis around the center of mass. This is not at all related to anything. This is just a fun fact thing. Another way to get I is using triple integration, but you don't need to know triple integration. And actually, you don't really need to integrate it that often at all, because if we think about it, we have mass moment of inertia formulas, right? And we look here, you're going to get usually something like this. You'll be given what the moment of inertia for different types of objects are as a formula sheet on your exam. Let me see if the one I had on my exam is here somewhere. I don't remember really what it looked like. This looks kind of similar. This might have been the statics one, actually. But whatever. You'll get a formula sheet that looks something like this. And, yeah. You won't have to actually do the integration or anything. It'll just tell you. And then this one even says along which axes these work, right? So this one's like more specific. Yeah, you'll be given the equations for all moments of inertia, so you don't need to worry about deriving them, right? So something big with moment of inertia is parallel axis theorem, right? So center of mass is usually the most common point of interest. We can also, of course, look at other parts of the body, right? And I was a function of r, and r has changed, right? So if r is changing, that means that the moment of inertia here, or with this r, won't be the same as the moment of inertia here with a larger r, for example, right? So we're going to define a new point A, which has, and we're going to, like this point here, we're going to call this A. This is A, and we're going to say it has an R as well. And this is R2, this is R1. R2 does not equal R1, so R1 does not equal R2, right? So that means that IA and IG can't be the same, right? And this is where parallel axis theorem comes into play. So the moment of inertia about A is equal to the moment of inertia about G plus a term here, md squared. Now what is d, you might be asking? Well, d is, and I'll switch colors here just to make things more clear. This is d. This distance between A and G is d, right? So factoring in mass times that distance, it's squared, right, is enough to basically make a parallel axis where you can get that, yeah, you'll get this as your setup, and then you'll calculate IA through this way, or you can calculate IG by subtracting MD squared, right? So there are a few things to consider. Is that IG, you cannot do this with IG as like the main subject. You cannot have IG is equal to IA plus MD squared, right? The reason for that is that IG is the lowest moment of inertia of the body. Because if you think about it, the moment of inertia around the center of gravity will be the weakest, the lowest, right? Because that is the center. That's where like the rotation is most likely to occur. So you probably have the least resistance there, right? And another thing is that this only works around the center, like with one of them being around the center of gravity. You cannot do this with like trying to get a parallel axis around another point B, for example, right? It only works when you're relating it to the center of gravity. So two things to keep in mind. IG is always the lowest, so it can't be the subject of the theorem. And this only works with IG, right? And now that's parallel axis theorem, which I forgot to label. Parallel axis theorem, right? Now we can go back to kinetic energy because we've learned about what I is. So we have this r squared dm right here. That means we can change this into an I in our kinetic energy equation, right? So for translation, we don't really worry about this stuff, right? We just have, so for translation, and this is all focusing on kinetic energy. So kinetic energy, I don't know why I put an arrow, but whatever. For translation, we have T is equal to half mv squared. This is unchanged for translation, right? So for rotation, we're going to have our this integral here, dt is equal to half omega squared r squared dm. But now we know that r squared dm, the integral of that is equal to I. So we're going to get that t is equal to a half I omega squared. As you can see, we're replacing mass from translation with I, and we're replacing v with omega, right? And this is about the center of gravity, right? So I should put this as Tg, and this is as Ig, like so. Rotation about center of gravity. And then if we have a rotation about a different point, so rotation about not center of gravity. We're going to get that T is equal to, again, we have whatchamacallit. This is total kinetic energy, and this is a sum, which is T of translation plus T of rotation about the center of gravity, right? So this is T is equal to half mv squared plus half, and this is Ig omega squared. To simplify this, we will just use our relations to make this all into one term instead of two terms. I guess it's still two terms, but there's like a factor out front. We get T is equal to, so half m w squared r squared, plus we're plugging in this theorem now. No, we're not. I was kidding. Like this, half of Ig omega squared. And as you can see, we can take out omega squared, right? T is equal to half omega squared mr squared plus Ig. And what are we noticing here? Ig plus mr squared. Well, that looks a lot like the parallel axis theorem, right? So we can just replace this with I about any point. We're going to call that point A, right? So that is our equation, half omega squared IA. This is for rotation about A. Like, it's the exact same thing as rotation about the center of gravity. You just have to prove it. And while we're here, we've also just brought up something, which is that the total kinetic energy of a rigid body is its translational kinetic energy plus its rotational kinetic energy. That's important to keep in mind, right? So, next up is work and like other energies, right? So, we already know what work is. This is exactly the same as what we did in chapter 7. So this section is just a review, really. So I'm not going to like really go over it that crazily. We have, remember, work is just fs cosine theta, right? And if there's a variable force, you just integrate it. If it's constant force, you don't integrate. There's work of weight and work of a spring, right? But so that's all stuff in the chapter 7 video, so I'm not going to go back over that because a video for that already exists. There's also forces that don't do work. So forces that are perpendicular to displacement and also friction on a body that moves on a surface without slipping, those don't do any work, right? So we're going to get into something new though, and that is work done by a couple moment. Now, a couple moments you should have learned in like statics, right? But I'll reintroduce it anyways. A couple moment is the rotational movement, right? So couple moment is rotational movement produced by two equal and opposite forces separated by a distance. You can denote this distance with whatever variable, right? So this is basically saying, and let's get rid of this ugly mass here. We have one moment going this way, and we have one moment going this way. They're equal, and that's going in the same direction. Going this way. They are equal and opposite, and they're separated by distance d. This is a couple moment, right? Very nice. So we know that a moment is force times distance, right? And yeah. So couple moments do translational work from the forces, and then there's work from the rotations, right? So for the translational work of the couple moment, we have that du is equal to f ds minus f ds. And this is denoted subscript t because of translation, but that doesn't matter. I'm not going to write that. As you can see, the translational work is just 0, right? And for the rotational work, we have that du is equal to m, which is a moment, d theta, right? So that means that the work done by a couple moment is just equal to, yeah, so the work of a couple moment for a constant couple moment, I'm going to add here, is m delta theta, right? That's for constant. Obviously, if it's a function, then you're not going to get this. You're going to have to use this integral here, right? But yeah, that's it. That's the only new concept here. The next things to come up again are just review, right? It's principle of work and energy and conservation, right? These are the exact same things, right? We have the principle of work and energy, and then we have conservation of energy. We have work being put into conservation of energy, right? So this stuff has already been discussed before in a previous chapter, so I'm not going to reiterate. Everything you need to know about work and energy will be in that video. It's just this new work done by a couple moment that we need to consider. So that is everything for chapter 12 in terms of the theory, right? Some of these chapters have been short, but now chapter 13 is a very long chapter. We're going to be learning some new stuff instead of just having a chapter filled with review. Anyways, hope you learned something. Thank you for watching. Bye.